Today we're going to look at some examples that combine the law of conservation of momentum with the law of conservation of energy. A classic example of that is Newton's cradle, and you've probably seen your teacher do demonstrations with Newton's cradle here. When you have a steel-on-steel collision, it's highly elastic, and for the most part, kinetic energy is conserved. And that's why the balls will bounce along for so long, because kinetic energy is being conserved. But of course, in any collision, you also have momentum conservation. We're not going to look at the details here, but the overall picture, if you have two masses that are the same, and you make an elastic collision between those two masses, and we're always going to have our incident ball coming in with a speed v, and the second ball is at rest. Then in the case where we have equal masses, this first mass will come to rest, and the second mass will take off with the speed of v. You can try that on a tabletop if you take a couple of nickels and slide one into another, making a head-on collision. You'll find the first one comes to a stop and the second nickel takes off. Now, let's say you've got a smaller mass hitting a slightly larger mass. What's going to happen then is you'll get some recoil, and afterwards the smaller mass will head backwards and the bigger mass will head forward. In the third case, where you have a bigger mass coming in and hitting a smaller mass, both will end up moving in the same direction. The larger mass will slow down considerably, and then the smaller mass will take off with usually a fairly large velocity. Okay, here's an example where we're going to combine both momentum and energy conservation. Perhaps you'd like to try this problem now and then come back for the answer. So if you're going to do that, please pause the video now. Okay, so the momentum of the system before has to equal the momentum of the system afterwards. And before, it's the big fish that's got all the momentum. He's got a mass of 2 times a speed of 3. So he's got 6 units of momentum. And then afterwards, here's the after scenario, we've got a grand total mass of 2 plus 0.5, 2.5 kilograms, moving at some speed v. That allows us to solve for v. It's going to equal to 5 divided by 2.5, and the original numbers were given to 2 significant figures, so I'll give my answer to 2 significant figures, and it is going to be 2.4 meters per second. Okay, now when we move on to part B here, how much kinetic energy was lost in the process? Well, let's see how much kinetic energy was there originally and how much kinetic energy there was after the collision. So originally, let's do the before. It's going to equal 1/2 the mass of the big fish, which is 2, times the big fish's speed, which is 3, all squared, plus the other guy's not moving. He's got no kinetic energy, so we get a grand total there of 9.0 joules. If we look after, then the kinetic energy will equal 1/2. Now we've got the combined masses, which is 2.5 kilograms, moving with the speed of 2.4 meters per second, and that'll get squared. And when we multiply that out, we're going to get 7.2 joules. So how much energy was lost? Well, just the difference. How much kinetic energy was lost? Just the difference between those two values. So the Ke lost will be 9 minus 7.2, or 1.8 joules. The classic example of where we combine momentum conservation and energy conservation would be the ballistic pendulum. Ballistic pendulums are used to measure the speed of bullets. So we've got a little bullet here. It's got a mass little m. And we've got a fairly massive block here. we've got a couple of stiff wires coming down, and there would be hinges at the top and the bottom, so that you get a nice smooth movement when this bullet embeds itself in the block. This length here, it's going to be fairly long because we want the bullet to be fully embedded in the block before the mass begins to lift. And if we've got long wires here, then the circle is going to have quite a large radius, and so the block can move a little ways before it really begins to rise up. Okay, so let's define our variables. We're going to have the bullet having a speed v initially, and then when the bullet embeds itself in the block, we're going to say that the speed immediately after that collision, after it embeds itself, is vbb, for v of bullet plus block. And then of course we got big M for the block and little m for the bullet. Okay, let's go on to stage 1 of this problem, where we're going to apply the law of conservation of momentum. And remember, in any collision, we will have momentum conservation. And what that means is that the momentum of the system before will equal the momentum of the system afterwards. And before, the bullet had all the momentum, so its momentum was m times v. Afterwards, the bullet embeds itself into the block, and they become a combined mass, big M plus little m. And they're going to move off with a speed vbb. So we would like ultimately to solve for this speed of the bullet. That's what we're after. So let's rearrange this expression so that we isolate the speed of the bullet. So we would get that the speed of the bullet will equal the combined masses divided by the mass of the bullet multiplied by the speed of the bullet plus the block immediately after the bullet embeds itself in the block. Let's go to part 2 now. Part 2 is where we're going to use conservation of energy. So we've definitely had all kinds of energy dissipated when the bullet embeds itself. But once it's embedded, the bullet in the block will have a certain amount of kinetic energy. And there shouldn't be any significant losses to the environment from that point until the bullet plus the block system raises to maximum height. So we've got system. Let's say that the bullet has just embedded itself in the block. So I'm going to call this sort of the bottom scenario. And then in the next scenario, I'm going to have the bullet plus block up at maximum height. So for conservation of energy, it's everything that happens after the bullet embeds itself. So I'll call this the top scenario, that's the bottom scenario. Now, if we have conservation of energy, that total energy at the bottom must equal the total energy at the top. At the bottom, and what we're going to do is we're going to call that line there, we're going to call that height equals 0. And it'll go and lift itself to a height h. At the bottom, there's no potential energy because it's at h equals 0. It's got nothing but kinetic energy. 1/2 combined mass moving at a speed vbb, all squared. At the top, it's got nothing but potential energy because at the top of the flight it will have 0 speed. So then we've got the combined mass times g times h as the gravitational potential energy. We can do a little bit of dividing out the masses, and we'll get that vbb is equal to the square root of 2gh. Remember, my first equation was v equals m plus m over m times vbb. So what I'm now going to do is take this expression for vbb and put it in here, because then I'll have all quite easily measured quantities for the speed. So the expression that I'll get is that the speed of the bullet will equal that ratio of masses times the square root of 2gh. As a numerical example, let's plug some figures in to figure out what the speed would be if we sent in a 5-gram bullet and it caused a 1 kilogram block to lift to a height of 10 centimeters. Okay, so we're going to have to use MKS or SI units. Big M is going to be 1.00 kilograms. Little m in kilograms will be 0.005, and the height will be 0.10 meters. So we'll get, and when we do that, we get an answer of 280 meters per second for the speed of the bullet. And that's all for today, folks. Thank you very much.